All right, good afternoon, everybody. We're going to go ahead and get started here. Welcome to another of Potter's partner webinars. Today we welcome Dean Russian, and he's going to talk about FFE's line of optical flame detection.
Thanks, James. Hello, everyone. Hope you're having a good week so far. Today we're talking about optical flame detection. I'm Dean with FFE, Applications Engineer from the Americas region. Questions can go in the chat. We can monitor those. There's also a Q&A section, so either way, put the questions in there. So the agenda for today is an overview of the technology, but first a quick intro on FFE, the company, and why that's relevant. So without further ado, let's proceed here. We are FFE, over 50-year-old company. We were founded as firefighting enterprises when we were doing mainly aviation extinguishers with halon. We pivoted about 30 years ago into specialty detection. We're probably most well known for our beam smoke detectors under the FireRay line of products. We also offer linear heat detection as well as optical flame detection, which we're going to be talking about today. The flame detectors are under the Talentum product line. That's how I've heard it pronounced. That's how I pronounce it, but you can get creative with the pronunciation of it. And we are part of the Halma group of companies. We have 50 or more sister companies that we do enjoy collaborating with, many of which are in the fire and life safety industry. You'll see some logos you might recognize there. It's a laser pointer. Here, I'll turn this off. So our company history is extinguishers, then in the 90s developed a beam smoke detector, and since then have developed a lot more technologies as far as beam smoke detectors are concerned. 2010s, we acquired the Talentum company and the manufacturing of that. All of our manufacturing for these products is done in the UK, where our headquarters is. And we also have a test center where we can do live fire testing. So that aids in the development as well as the compliance aspects. And we have worldwide approvals and certifications. Each of our products is also 100% inspected and tested before it goes out the doors. And as somebody who handles the tech support aspects, that's something that I appreciate, and it is exceedingly rare to find a defective product from the manufacturer out there. So optical flame detection, and we'll talk terminology on that, how you might see it in the codes and standards and things like that. These are devices that do detection of fire, unwanted fire. And so the agenda is we'll go through the what, where, why, and how, as well as some of the who. There's some unique capabilities with the Talentum product line that you won't find anywhere else as far as flame detectors are concerned. Various application examples are sprinkled throughout, along with code guidance or standards, including FM data sheets. There's something new that's very relevant for flame detection in International Building and Fire Code 2024 edition. Talk about that. When designing with flame detectors, we'll talk about some best practices, what those codes and standards say, as well as how to do your testing, what kind of options you have there. So a flame detector in the fire and life safety industry is something that is sensing or detecting unwanted fires. This is sometimes confused with flame monitors, are also sometimes called flame detectors. And that's more in the industrial realm when a flame monitor is checking for wanted flames. So think of like a pilot light or something like that, where you have a flame or a fire in an application. It's making sure it is there when it's wanted. These are detecting unwanted fires, flames. So the NFPA 72 definition of a flame detector, radiant energy sensing fire detector. And you will see it worded that way in many of the NFPA standards as well as FM data sheets. So keep a lookout for that. It might just say radiant energy sensing fire detector and not flame detector. So a flame detector, how is it different than other detection devices? Well, it's detecting the light that's emitted by the fire itself. So the light that's emitted by a fire, we can see a lot of that energy or that those photons that are emitted from a flame itself are in the visible spectrum, so we can see them with our eyes. A lot of that energy is emitted in wavelengths that we cannot see with the naked eye. So that includes infrared, that includes ultraviolet. So it's sensing all of those different things, and what it gives you is rapid detection. So within seconds or less than a second in many cases, as opposed to if you have a smoke detector, you're waiting for the smoke to build up, that being a byproduct. You're waiting for a smoke plume to behave in a semi-predictable way and travel into where you're sensing it from. So with it being a line of sight device, we stress line of sight because it needs to have a line of sight directly to the flame itself, not just any of the byproducts like smoke plume. So it needs to be the light that is given off from the flame itself. And if it's blocked by temporary obstructions or other types of physical obstructions, especially solid objects, it may not or probably won't detect. So direct line of sight, we know light moves in a straight line, so it is important to have that covered. And we'll teach you how in this webinar to properly cover different areas. They are great because you're not relying on, like we talked about, smoke behaving in a certain way, which can be very unpredictable. So you can have super high airflows, and it's also good at detecting through smoke and clouds of dust, fumes, different things like that. So the thing about infrared, you may even notice from your TV remote, it doesn't have to be pointed directly at the TV, or it might even be able to be blocked by certain things and it will still work. So there is some penetration that can happen with the infrared energy. And we'll talk more about that as well. The main applications for optical flame detectors, we know oil and gas is a very big industry. One of the biggest, I think, in the world. So lots of flame detectors used all the way along that supply chain or along that production process, from crude, offshore rigs, refineries, more midstream stuff, as well as all the way to the dispensers for consumers. You have different industrial applications. Paper and textile is actually the Talentum company was founded by the owners of a textile mill for their use in that application. And we'll talk more about paper and textile later on, some of the standards involved. You have aircraft hangars. Optical flame detectors have been a very integral part of designs for aircraft hangars for many decades. And we'll talk about some of the latest developments with that, as well as what people are currently using, what we're seeing for aircraft hangars. General industrial can cover lots of different things. Hydraulics, you have conveying, you have various hazards. A lot of it is insurance driven, but not always. Sometimes these are used as life safety devices. So FM really does carry a lot of weight when it comes to optical flame detectors. UL really doesn't get involved with optical flame detectors, although it can be used as a life safety device. Then you have battery areas. Some of the newer or the latest edition of International Building Code, International Fire Code, in battery areas, they have some new language that includes flame detectors. So why would you use a flame detector? The obvious code or standard requires it. So this could be your various NFPA standards, your building codes, fire codes, and things like that. Could also come from an insurance requirement. We know FM has lots of data sheets, which standardize a lot of the fire protection and prevention aspects in factories especially. With optical flame detectors and the nature of the devices, when it comes to hazard types, when it comes to response times, these are typically heavily engineered designs that these devices are being incorporated into. It could also be a standard or a preference by a corporation, a tenant, for their buildings, just based on what it is that they have going on with hazards, risks, etc. But the common thread is typically that you need fast response time, and what happens after the detection occurs can vary, shutting things off, having suppression, simply alarms. That's going to vary, but fast response time is the name of the game, as well as prevention of nuisance alarms. So two very important factors. So I do put a lot of wording in these slides and try to highlight more of the main points. I'm not going to go too detailed into a lot of this stuff. These slides can be available at the end via email, etc. I think there will be a recording as well for your future reference. The field of view of an optical flame detector is essentially a 90-degree cone. This 3D depiction in the middle here gives you a good idea there. The range, or the maximum range for detection, is based on a 1 foot by 1 foot pan fire. And so this, the maximum range can be anywhere from 80 to 200 feet, depending on what device it is. But you can factor that. It's important to note that your maximum distance for any specific device is usually going to taper off or be decreased once you get closer to the edge of the field of view. So 45 degrees in any direction from where that device is pointed, you may not be able to go the maximum distance because it's kind of like your peripheral vision. So NFPA 72, they mention possible obstructions. They mention field of view to be assessed, to that designers, engineers know what the field of view is, know what the distances are, know what the hazard area is, factor all of that into the design. Also, the FM data sheet recommends overlapping of coverage. So you're typically going to see every spot in a hazard area be covered by at least one, if not at least two, separate detectors, just because of the nature of temporary obstructions and the unknowns involved with that. NFPA 72, right off the bat, they say there should be an analysis done, or an engineering evaluation as well. Important factors that get their own sections include matching the spectral response to the spectral emissions of a specific hazard or fuel for the fire. So if you have a solvent room, whatever the spectral emissions of that solvent is going to be, you're going to want to have a device that is capable of detecting that and matching those emissions with the responses. And also with optical flame detectors, they're having to make decisions very quickly. For human terms, I guess it's very quickly, but for a machine, maybe not so quick. But you always want to be conscious of the potential for nuisance alarms. So you have infrared and ultraviolet and visible light sources everywhere in lots of different places. Being conscious of those and doing an assessment of that is something in NFPA 72 that they recommend. And they give you 9 different factors that should go into your engineering evaluation. And the FM data sheet, they go into a lot of the same stuff. With FM doing the actual testing of devices, which includes testing with nuisance alarm sources. So a lot of that is listed out in the FM data sheet. So X-ray machines, arc welding, different germicidal lamps that maybe use UVC, considering the fuel, as well as matching the spectral response to the spectral emissions. So we'll talk about the different categories of fuels. There's 3 or 4 main categories that you can have a fire from different fuels as it relates to flame detectors. Essentially solvents, hydrocarbons, and then some gases like hydrogen that are all going to have different spectral emissions. So some of those fuels here, hydrogen is a unique one. It burns almost invisible to the naked eye. If it is a sunny day and you have a hydrogen fire, you may not be able to even see it with the naked eye. Hydrogen's being used in fuel cell technology. I know a lot of warehouses have started using hydrogen-powered fork trucks, so there's less downtime than regular batteries. Flame detectors come into play with that, as well as your other gases. And your solid fuel examples, of course, we know things that have higher susceptibility to fire and flaming type fires, paper, plastic, textiles, electronics, including batteries, which are becoming more and more prevalent. So how do flame detectors work? You have this graph here, which is the electromagnetic spectrum, and this small gray shaded portion is the only sliver of the electromagnetic spectrum that the human eyeball can see. So that is called the visible. Everything else, human eyes cannot see. In the infrared, you can see that the spectral emissions of a gasoline fire, there's a lot going on. You have these different peaks and valleys, especially so you have what's called the CO2 spike. For your hydrocarbon type fires, at 4.3 micron wavelength, there is a very defined peak that's sometimes called the CO2 spike. So vast majority of optical flame detectors that are out there, they gear their detection towards this 4.3 micron CO2 spike. That's great for hydrocarbon and some other types of fuels, but there are other types of fuels like hydrogen that have no such CO2 spike. So something to be conscious of when selecting devices, etc. So each group of fuels is going to have similar spectral emissions. like this gasoline fire will look similar to any of the other hydrocarbon type fuel fires. And solvents as well, kind of group them together in a rudimentary way. With detection, prevention of nuisance alarms or nuisance detection is paramount. It's one of the most important factors. Because all environments are different, there are different false alarm sources. The sun emits UV as well as IR. A lot of these flame detector devices are used outside, which is okay and they work great. But selecting the right configuration of sensors can be that much more important. So FM in their testing, and this is not FM's graph or anything like that, but this gives you an idea along the top row, some of the more common nuisance alarm sources, some of them involving sunlight, like a sunrise or light shimmering over the water. Probably applies a lot more for oil rigs and things like that. But you have different lights flickering, you have welding. Arc welding typically is the type of welding that you want to be most concerned with when using flame detectors. There are ways to mitigate that or shield off arc welding causing any potential false alarms. But you can see optical flame detectors, if you've looked at different options on the market, they can just be basic UV with one ultraviolet sensor. They can have one infrared sensor. You can have two infrared sensors, 3 infrared sensors, and you're sensing all along those peaks and valleys that we saw in the electromagnetic graph. There's also combinations of infrared and UV. And some of them might even cross into the visible light spectrum as well. And typically, you can see the more sensors that you have, the better false alarm rejection you'll have. And that's not always the case. It's going to depend on the environment, on the false alarm sources. So what is unique about the Talentum line of products is that it's kind of a one size or one detector detects all flame detector. So as we were mentioning, the CO2 spike being at 4.3 microns before, with these 3 main fuel categories, you have petroleum or hydrocarbon, also it's called, methylated spirits or your alcohols, solvents, things like that. You can see both have that very defined CO2 spike. Hydrogen is one of the unique ones, does not have that spike. So if you're using any old flame detector that is geared to 4.3 microns, like most flame detectors are, you run a very high risk of not detecting it. So with Talentum, it is sensing more in this region of the infrared spectrum. So near IR covers your hydrogens, hydrocarbons, and solvents. So with Talentum as well, if you have, say, 3 IR is one of our common flame detectors that we offer, which means there's 3 IR sensors. Each of those 3 infrared sensors need to sense or detect the flame or the light, the photons given off by the flame. Not only do all 3 need to detect them, but they also need to be in the right proportions. So for certain sensors, you could need to see 3 times higher energy amounts than another wavelength. So it's comparing the level of signal that it's getting to one another. And so that is one of the verification methods that helps prevent false alarms. Also, it makes sure that the signal that it is getting is a random flickering, because natural flames flames are going to have a random flicker frequency. If you think of a strobe light, that's going to have a constant frequency. It will reject anything with a constant frequency. If you think of sunset, if you put a shop fan in front of that sunset, it will create that strobe effect, but at a constant frequency. That is something that is rejected. So just some of the methods in the firmware of the devices where it's verifying and helping to prevent false alarms or nuisance troubles, nuisance alarms. So another unique aspect with Talentum, ignoring the 4.3 micron CO2 spike that most other flame detectors focus on, is that in that wavelength or near that wavelength, you have glass absorbing or completely rejecting any light trying to pass through. So we can see through a plate of glass, no problem in the visible spectrum. But in other wavelengths that we can't see, it might be as opaque as anything. So that is the case with the 4.3 micron spike. It is almost completely blocked by plate glass. So a lot of these devices that focus on that wavelength, they'll use other types of materials for their lenses, like sapphire and quartz and things like that. So with Talentum, you can, it has been proven through third-party testing that it can detect fire through plate glass as well as clear polycarbonate. And we're going to go into more detail on that testing. And it's by no means approved or certified at long distances, but as a proof of concept, it does have the ability to, at a very good performance, detect through glass and clear substrates like polycarb. So here was the test. You have University of South Carolina, Aiken, testing in conjunction with a nuclear facility. And the interest in the testing was they have these glove boxes. If you think Homer Simpson with the glowing yellow cake, uranium, or whatever it was, on mounting devices inside of these glove boxes, or if you think environmental chambers that are glass, being able to mount detection outside of these is desired. So the test was set up at about a 6-foot distance with the either plate of glass or polycarb put right in front of the Talentum IR3 model alongside a video flame detector. So another device that's available on the market. It was thought that since the video flame detector can see through glass in the visible spectrum, no problem, that it would do well in this test as well. But it turned out the Talentum IR3 outperformed the video flame detector. So the triple IR, or the IR3, is the configuration of 3 separate infrared sensors. And this is, you'll see 2 different photos of these devices throughout this presentation. This rectangular blue one is a non-explosion proof housing. It's still cast metal and has good ingress progression or IP rating and things like that. But we found that many applications, even if you have a hazardous location, or even if not, explosion-proof devices are not always needed. So we've compiled, I think, over 10 or 12 projects where the assumption was explosion-proof devices were needed that were rated to certain hazardous classification, when in reality, based on the actual project specs or based on the location of the devices in relation to the actual hazardous area zone, that was not needed. And so you can save a lot of money by going with a non-explosion proof housing, still cast metal. So those are available, and we do pass that cost savings on to you if you are dealing with those kinds of projects. So those projects run the gamut from laboratory, oil and gas, heavy industrial, light industrial, wide range of that. So if you're interested in that, we can provide more info. So all of that false alarm prevention, all of those verification steps based on the 3 sensors, sensing the right amount of energy in the right proportions to one another, as well as sensing a random flicker instead of a constant frequency. And here shows the difference between our non-explosion proof or our standard model, which is the blue rectangular housing, as well as we do offer the explosion proof to class 1 div 1, and that is the EXD model. So a big price difference there based on materials and certification and things like that. And if you're using a lot of devices, the cost savings can be quite significant. So the IR3 model is available in non-explosion proof as well as explosion proof. Then the other sensor configuration that we offer with Talentum is 1 UV sensor and 2 IRs. So instead of 3 IRs, you're swapping one of those IRs out for an ultraviolet sensor. And you may see better false alarm resistance when doing this in full sunlight, fully outdoor type environments. One potential drawback of going with the UV as opposed to all infrared is that you won't have as good of penetration through dust, smoke, and other airborne contaminants. So FM approval is a given. Pretty much all of the US flame detectors that are used in the market are going to be FM approved. That's kind of the standard or benchmark for flame detectors. And the UV IR2, same concept as the IR3. Could do a little bit better for you in those high sunlight areas, fully outdoors. We have people that use the triple IR, the IR3, fully outdoors, even when when it's facing towards a sunset over shimmering water, and they have never had any issues with false alarms. So might give you a little bit better resistance there. And accessories that you might look at if you're doing a design with flame detectors. Usually the mounting brackets, but you're going to get those with pretty much every project, especially with the nature of flame detectors and their field of view needing to get that dialed in towards a specific place within a hazard zone. Weather shields, very common for outdoors applications, bale yards and places like that. Also, sometimes the weather shields might be used as field of view restrictors. So like a horse with blinders on, if you have a welding area off to the side, they might be doing arc welding and you want to prevent any of the energy from that arc welder getting into the detector, causing a false alarm, you can use these to kind of square off that field of view. Test simulator, this is a handheld thing, LCD screen. You select what kind of detector you have, you hold it about 10 feet away, and it is able to simulate the UV and the IR energy from a fire to put it into a false alarm. So always make sure to isolate the devices before doing so. And air purge adapters, this is a little less common. They are available if you have a high dust area or something like that. So aircraft hangars, optical flame detectors have been a staple in fire protection designs in aircraft hangars for many decades. I want to say at least 3 or 4 decades, flame detectors have been relied upon heavy in these areas. It's been pretty much the untold standard as far as detection goes in the past. So in a lot of these aircraft hangars, you're going to have some kind of deluge system. So it could be some kind of foam, high expansion, low expansion foam. A lot of that's changing with restrictions lately, or it could be a water type deluge. And doing the initiating for the deluge in the past has been optical flame detectors. And so one small hangar or one large hangar may have dozens of flame detectors. And the design is based on the scenario of jet fuel leaking out, igniting, causing this big fire, and it needing to be extinguished immediately. So really beefing up those systems to do that without anyone ever stopping and saying, hey, maybe we should assess the effectiveness of these types of systems and how we're doing things. So University of Maryland, along with Pool Fire, they compiled all the data that they could get their hands on from about 30 years worth of foam discharge incidents. And they came up with about 300 incidents, and there were only a handful of actual fires. So I want to say 5 or less actual fires, which caused 0 injuries and were extinguished quickly. On the other hand, you had over 250 incidents of false discharge or accidental discharge of foam and whatnot. Many of these could have been caused by a nuisance alarm from one or multiple optical flame detectors. And it was what stood out the most to the industry is that not only were these accidental foam discharges causing so much damage to property, millions and millions and millions, but there were actually more injuries and 1 death from the accidental foam discharges than any actual fires. So that's caused the industry, I think, to really stop and reassess a lot of these methods and a lot of these systems. So what we're seeing is not just optical flame detectors cross-zoned where you need at least 2 of them to initiate before doing a subsequent process, but also having additional detection types. So what we see a lot is optical flame detectors and linear heat detection. It's pretty common in aircraft hangars, at least the ones that come our way. And there's a more holistic approach. Instead of just beefing up everything with optical flame detectors, scaling that back, including another detection type, and maybe even having an additional manual verification step before any high or low expansion foam is dumped on the aircrafts, causing all of that damage to property. So in aircraft hangars, you're going to have lots of overlapping coverage, especially if you have a suppression step actuated by it. In this 3D rendering here, you can see a flame detector at each of the 4 corners, 2 on the sides, and then 1 on the top. So some hangars and for some aircraft, they may want under wing protection and over wing protection. or detection, I should say. So the mounting locations of your devices will depend on what the needs are. There's also a difference if there's maintenance activities happening in a specific hangar. May need additional detection. So moving on here to batteries. And this is not just battery energy storage systems, or sometimes called BESS, where you have these big batteries that are storing and generating power, transporting power. We do see those in a lot of odd spots now, not just in remote locations, but they can be in parking garages sometimes. If a high rise doesn't have the real estate, we see them as backups in data centers a lot of times. So there are the battery energy storage systems, which has been a hot topic in the fire protection engineering industry. Recently, the best and brightest minds are working on that. But also just lithium metal batteries that are passive, that aren't connected to anything. Maybe it's even in a box being stored in a storage warehouse somewhere. The new IBC and IFC 2024 edition, they don't make that distinction. They kind of, I think they're leaving the door open for each jurisdiction to figure out what they want to enforce. So I don't think that if you have a handheld drill, that they're going to have detection requirements for that. But if you have maybe a whole room full of these lithium ion batteries, whether they're in boxes or not, maybe being charged or something else, that may be looked at here very quickly. So still some generalities in this, but you have anywhere that you have lithium ion or lithium metal batteries in your storage occupancies, your factory occupancies, as well as retail and laboratory. Anywhere that they're being stored, manufactured, or tested, you need to have either aspirating smoke detection or optical flame detectors. So you have that option when it's an indoor scenario. If it's outdoor battery storage, then you no longer have the option to use aspirating smoke detection. And the only option is radiant energy sensing fire detection, which we know is flame detectors. So something to keep an eye out for. If you all have worked on any projects where this has come up, we'd be interested to hear more about that. Another example application, ignitable liquids, or this could be solvent rooms, any ignitable liquid really. A lot of detection types are mentioned in the FM datasheet, including optical flame detectors. So shutoff valves and things like that. Emergency power, running diesel generators or anything like that. You do want to assess how the shrouds might affect detecting a flame itself. If a flame is going to occur inside of a shroud, that might not be the best type of detection until the flame got big enough to spill out outside of any engine shrouds. Paint spray. We know not all buildings are created equal, not all manufacturing lines are created equal. They have several categories of paint spray. You can have individual booths, you can have automated lines, you can have, like this photo here on the right, drive in, drive out large booths. And then you also have your different types of paint that's being sprayed. So with powder coating specifically, if you have a powder coating line or a powder coating booth, optical flame detection, or sometimes you might be able to get away with a different type of detection. They have the requirement that the response time needs to be less than a half a second, just based on that application. Other types of paints, you may have a little bit more time, but it never hurts to have faster detection time. So they also mentioned heat detectors in FM datasheet for paint spray, and then there's NFPA standard for it as well, mentioning a lot of the same stuff. So with electric vehicles becoming more and more common, you have the fire protection and detection challenges that go along with that. This includes parking garages, where you have a mix of electric vehicles, internal combustion engine vehicles, and chargers as well. So these electric vehicle charging stations, and then in this same parking garage, you may also have a battery energy storage system. A lot of these standards are still being developed based on real world fire scenarios that have happened. A lot of it based on jurisdiction, not really to the point of having standards for this yet, but optical flame detectors are definitely in the conversation, as well as linear heat detection, especially with sprinklers and pre-action sprinklers becoming more common, especially in areas that can get below freezing. Recycling centers, they're going to be dealing with a whole host of hazards, hazard types. So that includes your batteries, your papers, textiles. Those textiles might have been soaked in ignitable fluids. So a lot of those types of things are coming in those doors. And optical flame detectors are a good, fast response way to detect those flaming fires, especially with everything being out in the open. Paper mills, in the FM data sheet, flame detectors are mentioned. We see them when the paper is already in paper form. We also see, you might also find it when it's in pulp form and it's being heated up and they're evaporating off the water. And a lot of those high temperature heater and those types of areas, spark detectors or flame detectors in those areas as well. But mainly when it's in paper form, it's going along in a web, high speeds. We've worked on several paper mills recently. I don't really know what the machine does, but I know the shoe press is kind of the moneymaker machine for these buildings. So you might have multiple optical flame detectors mounted with the shoe press in view. And you have different power generation type facilities, including hydroelectric power. Hydrogen fuel cell cars haven't really caught on yet, I don't think, in the US. Who knows what will happen? But I know that fork trucks and warehouses, they become more common due to less downtime. But in NFPA 2, for hydrogen specifically, you do have the detection requirement of optical flame detectors as well as leak detection and spill. I guess those are the same thing, and gas. So here's what a hydrogen fuel dispenser might look like. And you can see in each of these photos, you have a flame detector mounted up near the top. And you have other types of manufacturing, including food plants, which if you have a high-speed cookie or tortilla line, if one of those cookies or tortillas is on fire, you may want to shut that line down. So usually flame detectors, knowing that they're going into an industrial type environment, will have some kind of analog signal output for tying in with your industrial controllers, things like that. Hydraulics, if you have hydraulic fluid, that can become ignitable. And here we're getting to the last few slides. There are different options for testing flame detectors. So easiest is a remote test switch or just a key test station. Those are available for a lot of models that are out there. A lot of devices have internal self-testing, and what that's doing is checking for optical integrity. It does a sensitivity test. It may not give a good verification to an AHJ or to a technician who's looking to prove that testing was done, to just say, yeah, it's self-tested and it's good. Sometimes AHJs do want to see the bells and whistles. They do want to see panels show fire, or they want to see something more concrete than just it was a self-test. So there is the handheld test simulator. The Talentum devices are also doing self-testing periodically, and most devices out there do. And then the least attractive option for most, unless you have the means and that's your thing, is doing an actual flame or an actual fire test. So probably can't do that in a lot of hazardous areas unless you change things around, or maybe it's before it becomes a hazardous area you're doing such a test. But that is a semi-annual test frequency, NFPA 72, Chapter 14. And I mentioned at the beginning that the maximum distance that any flame detector can reach or detect a fire, it is based on the standard size of fire of a 1 foot by 1 foot N-heptane pan fire. So keeping this in mind, when you're looking at a project, trying to figure out where to mount devices, how many, which one, you're always going to want to think about what size of fire do I need to detect. If it's the size of a Bic lighter, then you may need to mount your devices a lot closer. Otherwise, it may take some time for a fire to grow to the size of that 1 foot square pan fire. That is the standard. So something to keep in mind, the closer that you get, the smaller of a flame that it can detect and more quickly. The further away you go, if you have a giant fire, these will still detect them, but it's standardized based on the size, and that being a 1 foot square pan. So some best practice stuff is you need direct line of sight. I think that's a given by now. Sometimes mixing detection types is good. Overlapping coverage we know is good. As far as mounting angle, you have a 45-degree in all directions field of view. So typically you're going to mount it up maybe 8 to 20 feet on a wall. If you're doing wall mounted, you're going to be aiming that down at about a 45-degree angle. If there might be sunlight in the field of view, you can aim that even a little bit further down as well to keep the sunlight out of the field of view of the detector. And keeping in mind any obstructions, temporary or otherwise. And it's pretty common that you'll need at least 2 detectors to initiate before you have a subsequent process happen, especially with suppression and things like that. So that's called cross zoning, sometimes voting or 2 over N, meaning you need multiple detectors to verify that they are seeing a fire before something else happens. The use of field of view restrictors can help prevent false alarms or nuisance alarms. sun and weather shields, as well as air purge kits, keeping dust and other stuff off of the lenses. Sensitivities can be adjusted, and verification times can be adjusted too. So usually the longer your verification time, the more sure the device is going to be, and the more data it has to base its decision on, am I seeing a fire or not?
For more information about Potter products, please visit our website at pottersignal.com. To access additional training resources, check out our online training portal at academy.pottersignal.com. Stay connected with us on social media for the latest updates and news.